right, so let's get started. A bit about me, as Ian has said, I'm not from America or London or anywhere glamorous like that. I'm from Hamilton. I don't work at GitHub or Microsoft. I work at a company called the Gallagher Group, but we're a great company. There's probably about 100 people in R&D, about 50 software developers, and I've been there for a few years. It's really great. There's my contact details. Over the course of my career, I've coded in quite a few programming languages, lots of C# and C++ and Ruby and Objective-C and various other things. C++ is kind of near and dear to my heart. It's one of the things I learned first. So about this talk. This is an advanced level talk about C++. It's not a talk about computer science, it's a talk about programming. There's lots of code, as befits Codemania, I thought, and we'll go pretty deep into some stuff. So with that in mind, I'm assuming that you can at least read some C++, Java style, C# style code. Curly braces and semicolons is where it's at. If you haven't done deep C++, don't worry, hopefully you can follow along. So, out of all the things I could have possibly talked about, templates is what I chose. And to answer that question, I'd like to talk about what the essence of C++ is. So, there's a video from, I think, Going Native Conference, which is a sort of native code conference in America a few years ago by Bjarne Stroustrup, the creator of C++, titled The Essence of C++. And in there, basically, he said, his view, the essence of C++, kind of what its goal is, it's the point of it really, is a lightweight abstraction programming language. So if any of you have seen C++ code, lightweight is probably not the words that spring to mind. What he's referring to, and he went on to explain, he's talking about runtime. So the goal really is to say, let's give you the most power of abstraction that you can have with the least runtime overhead. Now, there are many languages like Haskell and all sorts of other things that give you better powers of abstraction than C#, but they impose a runtime cost for you. I've done enough C# now that I get annoyed at the fact that my objects are all 3 times as big as they need to be, and the code is not quite as good as it should be. C++ doesn't have those problems. And for me, the best way that I know of to, I guess, achieve that goal of creating abstractions with minimal runtime overhead is via templates. So, what is a template? This is a template. You've got a list class, and as Tony mentioned previously, you don't want to have to go and write the same class over and over and over again for a list of fruit and person and oranges and whatever. So what you can do is you can use a template, also known as generics in other languages. And what you do there is you can swap out the actual type, so you're not just saying list passing strings in, you pass in a T. Now, a convenient mental shortcut for this is I've made a class that works with many different types. You can also have template functions. You can say, I've made a function, and my function can accept many different types of arguments. That's a nice mental shortcut, but that's not what actually happens. What actually happens in C++, and to some extent it happens in C#, it doesn't happen in Java because Java generics are a lie. In C++, templates are code generation. When you use a template function or class, what the compiler's doing, it's effectively doing a fancy version of copy-paste. Now, copy-paste is bad if you have to do it. We want the compiler to do it for us because it's not going to screw it up. So what happens is it takes your template, like our list before, behind the scenes effectively does a copy-paste and swaps in the real types for the T. If you use it multiple different types, so let's say you've got a list of string and a list of int and a list of something else, the compiler is going to go and do its fancy copy-paste multiple times and generate you 3 different classes. These have nothing to do with each other than the fact that they were copy-pasted from the same source. Now, where C++ kind of diverges from that path is C++ lets you override the generation process. So rather than just saying, here's how you make lists, that's it, you can tweak it. You can say, if we want to, let's say we know how to store a list of ints more efficiently. We've got some fancy data structure internally that we want to use. What you can do is you can tell the compiler, when someone asks for a list of ints, use this slightly different way. And that leads to some really powerful things. So, I'm getting to our first demo. So, how's that for font size? Everyone all good with that? Yep. Cool. All right. So I've got 2 demos. There's sort of 3 kind of parts to it. What I'm going to do in all these is build a safe version of the sprintf function. Now, if any of you have used C or C++ before, you've run into printf, I'm sure. If you haven't, you've probably run into string.format in something like C# or Java. And what you're doing is you've got a string and you want to swap in numbers or whatever into the middle of a string and build some nice formatted output. Now, the C one, you want to take, and it also wants to take multiple numbers of arguments. So not just one or two, you just want any number of arguments that you can swap in. Now in C, that works by you get basically a random pointer to some memory and you have no idea what's there, and it's terribly unsafe. We don't want that. We can do better. So here's my safest printf function. And as you can see, I've used a template here. And so it takes a format string, and it takes one argument. Now the argument is declared as t, so convenient mental shortcut, I can pass in any kind of argument in here and it'll work. Remember, when I try and pass in an int, it's going to go and copy paste me a whole function just for dealing with ints, and so on and so forth. So what we do is we just look for our replacement token, %at, and swap the value in. We have to run it through a string converter though, because you can't just go and stick a floating point thing in the middle of an ASCII string. You've got to actually convert it to ASCII characters first. So separation of concerns, I've got a string converter as well. So if we run this, sure enough, it works. However, it's not really living up to its name. What we'd like to do is have multiple arguments. So we might want to vary the greeting. We might want to say goodbye. And we might want to say, not just have one nice day. We might want to have 2 or 3, or some variation. Now, obviously, this won't compile, because my method here is hard-coded to only accept one argument. So in the bad old days of C++, what you had to do is you had to copy-paste the function yourself, and you had to make another version, and you had to have another argument, arg2, and so on and so forth. You had to make a million overloads for all the different types. C++ 11 gives you a neat new thing called variadic templates. And what that does is looks like this. So we've got our original method, but we've got a ... here. And a ... means we're going to accept any number of arguments. It's not just one. And so the way that this works is the arguments come in here. The first one gets put into our first parameter. And whatever's left over gets stuck into this kind of ... thing. Now, you can't access that directly. But what you can do is you can just make a function called somewhere else. And the compiler's going to take the first argument off, put it back in. I recall doing similar kinds of things in Haskell and university years and years ago. So don't worry about the ... dots. You have to type them 3 times, and they're in different places each time, which is why I have a code snippet for that. But sure enough, oh, I get an assertion because my format string, I forgot to put the right number of %ats because I typoed one of them. So let's run that again. And sure enough, we can see, goodbye, Orion, have 2 nice days. We've now substituted in 3 template arguments as opposed to 1. And we didn't have to write 3 different overloads. So that's nice and all. But what we'd like to do also is pass in slightly more complicated arguments. So rather than just one person, let's say I'd like to have multiple people. So the way that you do that, the C++ standard list class, I guess, is vector. So we're going to make a list. Orion and Ian, why not? So let's go and we'll call it people. And we'll pass that into a function. And we get a compiler error. And what we see, the compiler error is up here. Basically what it's saying is, now templates, a bit of an aside, templates produce some pretty weird compiler errors. And the reason they do that is because in this place it's saying, what I'm doing to actually do the ASCII string conversion is I'm cheating. I'm calling into the standard library of ostring stream, and I'm getting it to do the work for me. It doesn't know how to deal with vectors. That's the problem. But the compiler's saying the problem, it's basically saying the error is here, when in actual fact, 2 or 3 levels up, you've passed something in that's bad. Now, if you look at I'm not going to do it here because we haven't got time, but these things on the surface look really horrible, but if you just read the full compiler log and see, next step, oh, there it is. So the problem is that it doesn't know how to deal with vector. So what we can do is we'd like to make another string converter that deals with a vector, and we like the compiler to pick that one. So this is that specialization that I mentioned before. So the way you can do it is like this. So in this particular case, this syntax here with the just empty brackets, that's what's called a full specialization. So what I'm saying is, whenever anyone asks for a string converter for vector of string, use this sort of blueprint template here. If they ask for anything else, use that. Now, that would work, but we don't want that. We don't want to have to write a string converter for vectors of ints and vector of strings and vectors of something else. We'd just like to make one that works with all kinds of vectors. So what we can do is do this. This is what's called partial specialization. So you're kind of narrowing partial specialization. You take the original template, which works with anything, and you kind of narrow it down a bit. So this is now going to work with anything with vectors. And here's one I prepared earlier. So all we do is we just implement the convert method. We'll just loop through all the items in the array, and we stick them all into a string with commas in between them. And that's pretty much it. What's gone wrong there? Non-const value to standard basic string char. Let's try that again. Template type name t vector t. So, backup plan. Here's one that I know that works. It's pretty much the same, apart from I've missed some minor thing. That's right, I have to take a vector of t there. And sure enough, it selects the right one. So go back to our slides and just a quick recap of what actually happened there. So this is what happens when you reformat your slides to 4x3. Right. So we called a function safe_printf, and we pass in 3 template arguments. What's actually happening is the compiler is going, well, you want a function with 3 template arguments. I've got this ... one, so I'm going to just make you one. Copy-paste comes in behind the scenes, makes you one with 3 template arguments. Now, what that function does, it takes the first argument and tries to put it in. And in order to do that, it says, I want a string converter for strings. So it just makes one of those. Then we do the recursive function call down to 2 arguments. Compiler goes and makes one of those. This particular one wants a string converter that knows how to deal with a vector of string. And so compiler just goes and makes one of those. And it sees our specialization and goes, I'll use that, thanks. And then likewise, we come back to the final argument, which is an int. And that hits our sort of termination case. We had our ... function, and at the end we had one with no ... And that's when you sort of stop recursing and you're done. So when should you use templates? By this I mean, when should you, I guess, write template code? Mostly it's useful for writing infrastructure. So this is what I guess the people who design C++ think of when they are thinking of how to design templates. They're thinking of people you're writing utility helper functions, libraries, frameworks, that kind of thing. Now, you may not write many frameworks in your career, many libraries, but you're probably going to write plenty of utility functions, particularly in C++, because it doesn't have a whole lot built in. And there's a lot that I've seen floating around which they only work with ints, or they only work with strings, or they only work with something. And you could quite trivially convert them into templates and have them be much more widely useful. But even if you never do any of that, you're still going to be using templates, even if all you do is make vectors. So it will at least help you understand compile errors to understand really what's going on. So a bit about the compiler's view. What does the compiler see? There's 2 sort of phases of compiling templates. The first is the template definition. So when your compiler loads your CPP file, it starts at the top and runs down and hits code, and as it goes, there's a function. I'll compile that. Now, for normal functions, it tries to compile the whole thing and does error checking and so on and so forth. For a template function or a template class, it can't do a lot of error checking because it doesn't know what the type of T is. That's going to come later. So it kind of just puts it off to the side and says, OK, remember that in case you want to use it. When it actually comes into play is when you actually write some other code that uses the template. That's called instantiation. And a key point here is that templates that aren't instantiated don't exist. Unlike normal functions and classes, you can write a template class that's full of garbage that won't necessarily compile. You can put static assert false in there and that kind of thing. And if you don't use it, it doesn't exist, it's gone. There's no trace of it in your binary output, and it won't produce a compiler error. And the other term is this term substitution. And that's just a way of saying when you instantiate a template, we're swapping in the real type, string or int, or whatever it happens to be, for the T. So what happens if you've got multiple templates? Like before, we had our string converter, the base one, which just worked with T, and we had our specialized one that worked with vectors of T. So the rules are, if a template definition can't be instantiated, it's ignored. So when we just say, give me a string converter of int, it says, oh, can we use that vector one? Nope. Don't try and do it. If we tried to do it, we'd get an error. So we just ignore it. That's fine. The technical term for that, brought to you from the same people who brought you RAII and other kinds of terrible C++ acronyms, is SFINAE. That stands for, I'm not going to try and pronounce it. I have no idea how you pronounce that. That means substitution failure is not an error. So yeah, if we try to instantiate it, if we can't, that's fine, let's move along. Look for something else. Now, on the other side of that, if there are multiple ones that could work, so when we're asking for a vector one, the base one could still, in theory, work. But the compiler's going to pick the best one by some definition of best. Generally, it does what you expect it to do. It's kind of like function overload resolution. If you've got two functions, it'll pick the one that most closely matches the arguments. Now, with that stuff, what you can do is you can put some of that stuff together and as sort of building blocks. So there's a trick here, basically. If you've got a type going in, and there are multiple templates that it could pick, now it'll do different things depending on that. You can kind of think of that as a compile time if statement. We put something in, and there's going to be some result, and it's going to be one of two or three, like an if statement. If you want to get something out at compile time, what you can do is you can declare a static field, or an enum, or you can declare a type def. And you can reference that. So in our string converter, we could have put a type def in there and referenced it from somewhere else, and then plugged that into something else. There's a thing called decal type, which is a fancy C++ keyword. Now, you don't have to use this, but it's kind of the easiest way to achieve some things. And what it is it's a keyword, and you put some code in between the brackets, and the compiler, and it's basically like a theoretical answering a question. If we would run this code that's in between the brackets, some kind of result would come out the other end. So typically use it with a function call. We say, if we would call this function, what would the return value be? Would it be an int or something like that? Now that kind of sounds a bit pointless and theoretical, but I'll show you something where it's actually quite useful. And the key thing here is that because templates can refer to other templates, we can feed these into each other. So we can have a template, I guess, function return value with a type def, and we can feed that into some other template, which maybe you've got multiple, so that's an if statement, and you can feed that into something else with another sort of typed in, type out. And what you get is actually a fully Turing-complete, pure functional programming language. Now, it wasn't intended to be a proper programming language, but as it turns out, you can compute anything at all in the compiler in C++ with templates. Just because you can doesn't mean you should, and it would be quite awful and disgusting, but there you go. So let's put some of that stuff to use. So this next demo picks up sort of where we were before. I've gone and made a printf function which just prints to the screen to avoid having to do it down here. But anyway, the key thing is what we'd like to do is we can print all of our basic primitive types and we can print vectors. What we'd like to do is print some other user-defined type. So in this case, I've got a person class. You might have a whole bunch of these classes. And what we'd like to do is, it's got a toString. We'd like to call that. So we want to feed that person into our printf, and we'd like it to call the toString method. So the way that you could do that, the way that you would do this in something like C#, Java, or indeed most other programming languages, is you might define an interface or a base class that says, I've got a toString method, and then you could make a string converter or a helper or something that says, I know how to deal with this interface. Now, that would work, and you could certainly do the same thing in C++ as well, but we can do better. Base classes suck. Inheritance is no fun at all. What we'd like to do instead is just have the compiler work it out for us. I don't want to have to put inherits this interface all over the place. I just want the compiler to say, do you have a toString method? Yep, go and call it. So, can we do that? The answer is yes, we can. And I'm going to show you how. So, the first thing, there's two problems there. The first thing we need to do is say, we need to make a string converter that calls the toString method. The second part is we need to be able to have the compiler work out for us, do you have a toString method or not? And if you do, use this particular string converter. If you don't, use something else. So how do you get the compiler to figure out, while it's compiling things, whether or not you've got a particular kind of method? So one of the ways that you can do it, there are lots of ways that you can do this, but the way that I'm going to show you today is what we can do is make a helper. We'll call it has toString. And it's a template. So basically, we're more or less writing a compile time function. So this is our input. A type comes in. So it's going to be person or string or int or something. And out the other end comes another type. So the way that you, I guess, return types from your compile time functions is with typedef. And we're going to return something. We're going to call it result. So what is that thing that we're going to return? Ideally, we'd like to return true or false. Now, true or false is not a type. You can return booleans if you like, but in this particular case, they don't fit. But what there is there's a thing called true type. And true type is basically just it's like a structure that only ever contains true. There's correspondingly a false type. This is just all in the standard library. That it's just a boolean that's always false. It's the type of a boolean that's always false. So we want that to return true. But we only want it to return true if you actually have a toString method. At the moment, it's just returning true all the time. So this lovely code snippet here does that. And let me explain how. So we'll start with the result and work backwards from there. So remember before I said decal type. Decal type says take this code in here and don't run it, because we're a compiler. We can't actually execute code. We can only compile things. But basically it says if that code were to run, what would the return type be? So what we're actually doing here is we are calling a function f and passing it null pointer. And we're also passing it a template argument t, which happens to be our input argument. So we're saying our input argument, pass that along to f and see what result it had. And the key here is that there are two f's. There is this one, which has a return value or a return type, a false type, and it has arguments of ... So it matches anything, pretty much. Anything you put in there, it's going to say, yep, that works. And on the other side, we have this. We have this other overload of f, which has a result of true type. And it has this sort of incomprehensible gibberish in here. It's incomprehensible because it's declaring a function pointer, and the C syntax unfortunately, the C syntax of function pointers is quite terrible. But what we've got here basically is there's this little helper struct here, which contains no code and does nothing. But it's declared to have template type of pointer type and likewise the same pointer type. So what that means is you've got a thing in the compiler, and the compiler, it's only valid if both sides are the same. So you could go eq int comma int, and that would work. The compiler would compile that. Or you'd go eq int comma something else, and that would not be the same, and so the compiler would, well, you can't logically produce one of those things, so you'd get some kind of error. And that's the key here. So what we do is we take one side of it, and what we try and do is, remember we've been passed a pointer, it's a null pointer. We try and say, it's a null pointer, but it's of type T, which is of type our class. So what we're doing is we're saying, get our class, and try and check if it has a member function, which takes 0 parameters and returns a string. And on the other side, we're saying, get the member function called toString. So one side you have a function pointer, does it have the right signature? On the other side, you have get a method called toString. Now, if those line up, and the only case that that will be true is if you actually have a method called toString that has the right type, then they'll result in the same kind of function pointer. Then our little equality struct will be valid, and that's fine. If they're not the same, so if there's no method toString, or if it returns something else, it doesn't return a string, then they won't be valid. The compiler won't be able to make one of our equal structs, and it'll be some kind of internal error. And what that will do, remember, the substitution failure is not an error. So the compiler will try and make one of these. If it fails, it won't error. It will just go looking for alternatives. And it will find this. So the end result of that, after all of that stuff, is basically saying this is either going to be true or false. It's going to be true type if you have the right method, false type if not. So the next thing we need to do then, now that we know if we have toString method or not, we need to make a string converter. So string converter. And what we'd like to do is have our string converter work on T's, but somehow we need to also say where it has a toString. So this is a bit of C++ weirdery, but basically the way you can do that, we want to specialize the template. We don't want to just accept any old T. We only want to accept T where toStrings are. So we need to take that base one and kind of narrow it down. But we don't want to narrow down the T. So what we need to do is we need to narrow down something else. So the trick to that is you declare an extra. What we do here is we declare an extra pointless template that we never use, template type that we never use. And what that means now is that whenever anyone asks for a string converter, let's say they ask for a string converter of int, there's actually 2 parameters here, and the second one gets defaulted. So they're actually asking for a string converter of int, true type. And so now what we can do is we can specialize. We can say, we can specialize on string converter of T, true type. So we just write our method. And all we do is return item.toString. So if we compile this, it's going to fail. Firstly, because I need a capital S. But secondly, because now it's saying member reference const char star is not a structure union. So the long of that is we're putting this in, and it's trying to call toString on that. The reason is we're asking for T, true type, and we always match this all of the time. We only want it to match if we actually have the right method. So we need to somehow plug this into here. So if we have a true, we want to plug a true type in, or a false type. And conveniently, that's exactly what this does. So let's plug that in. We need the type name there just because of a weird syntax rule. So what we're doing is we're saying effectively call this compile time function and stick the result in. So if we have toString, the result is going to be true type. And the compiler is going to go, yep, that's the specialization I'm looking for. If we don't have it, it's going to be false type. It's not the specialization we're looking for, and we fall back to the base. So let's run this. And sure enough, we can say, hello, person Orion. It's called our toString method, and it's worked. But for the other types, for the ints and the char stars and all the rest of it, it hasn't. Just to prove that this works, we can define some other kind of struct. Let's call it int wrapper, and let's go string to string, return aha. And let's make one of those instead. And you can see it just happens to call it. We didn't have to have any interface, there's no base class. It looks for a method at compile time and it just calls it. Now, because the other specializations are still existing, we can plug those into each other. We can make a vector of person. And we can put P in there. And we can put multiple people in there. And, well, there's only one in there, but you can see one feeds into the other and they all kind of work together. So, recap, what happened? When we ask it to printf 3, the compiler asks for, we need a safe sprintf that works with an int, that's fine. Then we need a string converter for it. So now it says, let's try and make a string converter. We've got 3 possible specializations. We've got our base one, we've got our vector one, and we've got our new fancy has2string one. So it's going to try all of them. And what it does is, first, so dealing with the true type one in particular. If we look, it's looking for a string converter of t comma true type, because our dummy makes it always look for that. It tries to resolve that now by feeding that into that has2 string. Now we feed into the has2 string, which feeds into the decal type, which feeds into this, and this results in garbage. And so the compiler goes, that's fine, garbage is fine, I'll just go looking for another template. And it uses the base template. For an actual class that has a toString, our person class, it does the same thing. It feeds the person into there, feeds the person into there, feeds the person into a equality structure, and that turns out to be valid. So the compiler goes, yep, true type is the result. Let's use that specialization. Simple as that. And all it's doing is just trying to effectively build classes for you by copy-pasting and picking the best one. So, starting to wrap up a bit. Templates are just code generation. Key term is the compiler is substituting things. Templates are defined when you see them, but not instantiated until some other code is using them. The terms I find are helpful because they tend to come up in compile error messages and things like that. When you see so-and-so instantiating, now you know what it means. And you can substitute specialized versions of code for sort of edge cases. Maybe you like handling vectors or more optimal implementations and so on. Templates can refer to other templates. As you saw, we can sort of feed one into the other. They can do it recursively. I didn't show you recursion there, but you can do that. And this lets you sort of execute logic at compile time. Fundamentally, it looks complicated, but fundamentally all you're doing is saying, here's these options, plug some types in, try and build them all, and just pick the best one, and throw away the ones that didn't work. So that, what I showed you before is, I guess you could sort of argue it's template metaprogramming or not. Most of the time, when people talk about template metaprogramming on the internet, they show you calculating factorial at compile time. Personally, I think a better way to calculate factorial at compile time is to calculate it in Excel or calculator and paste it in. However, one thing which was useful is I thought this was quite neat. So what we're doing here is a similar kind of technique. We've got 2 templates, and it's one calling the other. Except rather than a type coming in, a number is going in. And our, I guess, compile time function return value is doing some recursion. And so this kind of lets you write that. You can write binary blah, 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 colon, colon, value, and at compile time, the compiler does all that and just plugs 13 into your source code. You can do it with other things as well. There's an example that I saw on Stack Overflow of someone using this kind of technique to generate sort of bit masks for calling sort of obscure MMX functions and things like that. So yeah, I'm not going to demo that. We haven't got time, and it's even more obscure, but there it is. The point is, anyway, what really clicked for me is the sort of mental shift from, rather than just saying, I'm going to write some code and the compiler's going to just deal with it, the compiler is your friend. You can interact with the compiler. You can ask it questions. You can get it to do things for you. This is true of more languages than just C++. So even things like C# and Java, you can to some extent get the compiler to do things for you, so you don't have to. Don't worry about the syntax. That's what Google is for. Any more resources for anyone who's interested? There's a book called Modern C++ Design from 2001 of all things, but it's actually really good. It's got all kinds of sort of like little ideas and techniques and things. Most of them use templates, but it's not about templates. It's about sort of design. Any of the videos from the Going Native conferences I'd highly recommend. And the C++, just recently, C++ standard has got a FAQ. And what they've done is they've merged Bjarne Stroustrup's FAQ and a couple of other ones, and they've got this big, giant Uber FAQ. And it's actually quite well written. So if you want to look up more things about any of this, it's probably on there, and it's probably not a bad explanation. And there's many, many, many more resources. C++ has been around for years and years and years, and there's millions of articles about it, even more than Haskell. Thanks. Cool. Are there any questions? Do we have time for that, or are we good to go? Yeah, if there are any.
When you say the compiler's your friend, it doesn't look very friendly.
Yes. Some of that is an artifact of, I guess, how long C++ has been around and the fact that it's evolved. If you take out the fact that function pointers look like rubbish, then it's not so bad. Yes. Yeah. The key to those is, yeah, as I was saying before. Yeah. Compilers are getting better. I'm using Xcode here, which is Clang, and it produces much better error messages than Visual Studio does, which is what I usually use at work.
That's really what I was asking, so it's someone working.
Sort of. Obviously, the compilers will hopefully produce better error messages over time as the compiler writers improve them. C++, there's a thing called concepts, which was meant to go into C++ 11, and it didn't make it. It was meant to go into C++ 14. And what that's trying to do is let you, I guess, constrain templates. You can sort of say, I want a template that works like this and this and this, like what we had there with the has2 string, but with a much nicer syntax. And there's a thing called const expression as well, which provides you an easier way to write that kind of code. So that's coming in the next few years. Yes?
So previously in the previous session, Karen was talking about the pipeline abstractions. And we were saying how I was just trying to do that. I've noticed for specialization over a vector of T.
Yep.
Can you do that specialization over something, a T that contains something else? So regardless of something that you got a sense, other types of containers, you would have to repeat that type of tree with that higher abstraction.
Potentially you can. I'm not a Haskell expert, so I don't know in theory, but from the sounds of it, I think you probably could. You'd probably have to use some kind of hack like I did with the dummy extra parameter and the sort of helper class, but I believe you can. Yes?
Is it possible to say that spherical
Yes. Yes, it is. You can just have, in that metaprogramming example, template types don't have to be types. They can be ints or bools or anything. They can't be floats because floating point numbers don't equal each other, but they can be other things, and you can return a Boolean. Now, how you'd actually normally do that example is you would return a Boolean, and there's a thing in the standard library called enableIf, and enableIf does the, I guess, true type, false type thing for you. So yes, you can.
So does that mean you wouldn't have needed that dummy template?
You still need it, but you just use it in conjunction with enableIf. But yeah, you can certainly return. Yeah, if you don't need to return, like in this case, I was putting a type in and a type out. You can just return a Boolean if that works for you. Anything else?
It's usually one of your motivations was the runtime of code. How code is just more easy or one language. Why is that important to you? Why is that? If you're not paying down information, your developer resources are actually harder to scale than your runtime resources.
Yes, I see your point. And I've used that argument myself to promote the use of Ruby at the time, because that's what I liked at the time. But the answer to that is, I guess, scalability. There's scalability, obviously. If you're making a website and you have to serve 1 million people, if you can do it on one server instead of 20, that's a lot of money. Mobile is another example. If you're working in a resource-constrained environment, you may not be able to afford to use 2 gigs of RAM to run your program. You may have to use less RAM than that. And fundamentally, I don't know, I've written enough large-scale C# applications that I've started to run into problems as well. You just get annoyed. It's like, oh, these objects take 20K of memory instead of 3, and I don't know. It's more about the scaling up. If you're just writing sort of academic things or smaller things, you're probably fine. Does that help answer your question? Cool.